Good evening, ladies and gentlemen. Welcome back. It's been a while, 2 months off for the summer, but we are ready to go on season 2, it would seem, of Physics Rocks It's True. This evening we're going to take a look at graphs. We're taking a look at how to draw good graphs, how to calculate gradients from graphs, how to get equations of graphs, and use that y equals mx plus c wonder equation. I'm just going to take a look in chat here, check that everybody is still with me, that you can hear me okay, because it's been a while since I've streamed and I'm slightly traumatized by the setup because I'm in a new battle station. Pictures for that sometime later. So let's get to work. When you're drawing graphs, broadly speaking, your information comes from a table, and your table can be horizontal or it can be vertical. Let's take a horizontal table just for fun, and let's take a look at how that would look. So maybe we've got two things, A and B, and then we've got some numbers associated. So this has 5, 10, 15, and well, let's take a jump to 25 for just to make it as complicated as possible, because I'd like to think that everybody can, broadly speaking, draw a graph. Okay, let's do some numbers on the other one. Let's go 3, 6, 9, and then 15. So we should get a reasonably straight line graph out of this. Okay, so graph plotting requires a graph grid, so I'm just going to grab one here so that I can copy and paste it each time I need one, and shrink it to the right size. Oh, that was bad. And shrink it to the right size. Okay, so let's get that in there so we can see the table and we can see the graph grid at the same time. Alright, so tip 1 when you're drawing graphs is that your x and y axis should take up more than half the available plot area. That's a scaling thing. There are marks available for that in exams. Okay, so let's get some red lines here. So we're going to go across here. What have we got? We're going to start here. So we've got 1, 2, 3, 4, 5, 6, 7, 8 squares, 9 at a push. Okay, so let's take a little look here. Is there no arms that table you gave us? Sorry, yeah, the measurements are disgusting. Yeah, apologies for that. Right, thanks Matthew in the chat. Okay, so across the ways then we've got 1, 2, 3, 4, 5, 6, 7, 8 squares, and I want to go. Let's put this on the axis. I've got to get to 25. So how do you get 25 and 8 squares? Not easy, because you want to kind of go, oh, 3 is good, but no, that's a bad idea. So because I would only get to 24, and working in 3s is just terrible. Working in 4s, it could be done. We could go 0, 4, 8, 12, 16, 20, 24, 28. That's fine. But since this goes up in 5s, it makes sense to try and go up in 5s as well. So let's do that. Okay, so let's go. We'll take a 0 here. We'll take a 5 there. So this will be 10, 15, 20 over here, and then 30 over here. Okay, so my graph will end here. So that's okay because I'm over halfway along my x-axis, or halfway along my available plot area, so I can do that. So let's go up the y-axis here, and I've got 1, 2, 3, 4, 5, 6, 7. I've got to get up 8 in the y-axis, 9 at a push if I want to. 8, so I have to get from roughly 0 up to 15. Okay, so your immediate thought there should be 8, 16. So 2s looks like a pretty good. Shout for that one. So we'll start at 0, and that'll be 2, and this one will then be 4, 6, then 8 up here, then 12, skip 1, and then 16. Alright, and that's my graph ready to go. My graph's ready to go. Here I can start plotting points. Now plotting points, you'd like to think is a straightforward affair, but we've got one more thing to do before we do that, which is label our axes. Okay, so we don't make the mistake of labeling the wrong things. That's A across the bottom and B up the side. Always do that before you start drawing anything. If you have to label your axes, make sure that the labels are in there. And if you've got units, pop those units in too. That way you're less likely to accidentally plot the scales the wrong way around. And you wouldn't believe how many times that happens. Okay, so we go, A is 5, B is 3, so there's 5 there, 2's there, so 3's just kind of roughly in between that. And you will notice that even on a computer with dodgy kind of mouse control here, I'm drawing a little X. And the reason that we draw an X is that once we draw our line of best fit, if we do dots, the line of best fit will wipe out the whole thing. So it would wipe out your line, you wouldn't, or would wipe out your dots, you wouldn't be able to see them, and then an examiner can't mark them. And that's the kind of key thing. Also, if you're doing a CA exam paper in physics, that paper is scanned. Okay, so and if anybody scanned a document rapidly at kind of reasonably low quality, you sometimes lose a little bit of the graininess or a little bit of the fine detail that you normally get in photo quality stuff. Okay, so make sure that anybody who's coming to read your stuff can see exactly what you're doing. So we've got 5, 10, and 15 in there. We've got 25 to go here, which is on 15. So there's 14 and there's 15 there. So 25, 15. So that should be us here. Okay. Line of best fit then needed. Usually at GCSE level it's going to be a pretty perfect line, but you never know. You might get some dodgy points. So we want to draw, especially in the practical exam, you will get ones that you have to interpret. But that's pretty straight line. That's not bad, by the way, for freehand on a computer. I'm just saying. Okay, so straight along. Yeah, Mr. Smith last time I checked, but anyway. We've got a nice straight line graph going on here. Now what we really want to do with this is we want to figure out how can we generate all the values of B that there ever could be, How can you generate all the values, how can you fill in this table for infinity time with any value of A that you could possibly ever come up with. And this is where we introduce the straight line equation. And it's something that people who don't like maths get a little bit afraid of, but we'll try and break it down into something sensible. And the straight line equation is that y equals mx plus c. And that's math speak, so we want to turn that into something that we can actually use. So there, we're going to define all of these terms, we're going to write it as a sentence. Okay, so y, mx, and c. So y is the thing on the y-axis. Okay, so what have you got in your y-axis? What have you plotted up there? In our case, we've plotted b up there, so that's really what we're talking about. We're talking about b in our case, but it could be anything you plot on the y-axis. And normally that's your dependent variable, the thing that you're actually going out to measure. Okay. Now x, no prizes for guessing then, is the thing on the x-axis. And in our case, it's A, whatever A happens to be. It could be like area of a sheet of paper. It could be anything, right? But that's the thing that, broadly speaking, you're in control of. Okay, so that's what, if you're doing a timing practical, it's probably time. All right, so the other two then are the interesting bits. They're the bits that we actually need to think about. So M here, I'm assuming I'm in the right font. M here is called the gradient. Okay, and C is called the y-intercept. Now, everybody knows that physicists are the smartest people alive. Like that's just fact. And mathematicians are close second place. If you can't do physics, you do maths. So what we mean by gradient and y-intercept, that's smart people speak, because when you're doing a smart subject, you don't want it to appear that things that you do are simple. So we use a fancy word here for gradient. What we really mean is slope. Okay, that this is a number that represents how slopey your graph is. Is it really steep or is it really shallow? Big number, really steep graph. Small number, not a steep graph at all. And the y-intercept is where the line hits the y-axis. Now be careful, because if you've broken your axis, that's not quite the same as where it is on your thing. It has an x coordinate of 0. Okay, if you like your coordinate stuff. Okay, so where did it hit at 0? So let's take a look at these two concepts. So the y-intercept is straightforward. Right? You just go and look at your graph, come over here, get your eyeballs along this graph line, draw it all the way back, and go, boom, right? Where does this hit? Where does this hit the line back here? Okay, and it's kind of handy in our case. It hits at exactly 0. So y is 0 when x is 0. So we can say that the y-intercept is 0. That's awesome. Right, okay. Done. Walk away. The next bit, though, is a little bit more tricky. We now need to calculate the slope of this graph. All right. And calculating the slope of anything is done by comparing how far you go up by how far you go across. All right. Like it might be, there are people that go out running and like, oh, I did a climb of 500 meters. Whoa, that's impressive. 500-meter climb. Well done. Okay, they neglect to tell you that they did the 500-meter climb over a 7-mile period, and it's less. The 7 miles is actually quite impressive, but the 500 kind of thing? Nah, not a thing. You've gone 7 miles to get up 500 meters. That's nothing. Okay, whereas somebody told you they've gone up 500 meters over the course of a quarter of a mile. Okay, well that's certainly more impressive. It's in fact, like 28 times more impressive than the guy who was just going up a gentle uphill. And that's the thing. So what you're doing is comparing how far you go up with how far you go across. Okay, so one might say that you're comparing the rise that you're experiencing. Let's do that. So rise, and you're comparing that to how far you've run across. Okay, and when you compare things mathematically, you tend to do them as a fraction, so you divide them. Right, so the slope of the graph is your rise divided by your run. We're not going to use common words like slope because we want to make ourselves seem very posh. So we're going to say the gradient of any graph is equal to the rise divided by the run. Now we're going to make ourselves a little bit even more special in this one. We're going to say, rather than rise over run, we're going to stick a bit of Greek in there, because if we can use a couple of Greek symbols, we suddenly appear very, very, very clever indeed. Okay, so I'm going to stick this in. I hope this works. No, that's not going to work. Yeah, there we go. Okay, Greek capital letter delta, like a little triangle. And if we do delta and then a y divided by delta and then an x. Whoa, that was the wrong button, wasn't it? That is not an X. That is very cool looking though, but it is definitely not an X. So let's try that again. Delta X. That's better. Okay, and we're going to do delta Y over delta X. Now, mathematically, in all mathematical language, delta means changing. It's really weird because we use symbols for all sorts of different things, but delta, capital delta like this, always means changing. So what that says is change in Y divided by change in X. That's all. Okay, so what we're trying to do here then is find the rise divided by the run of our graph, or we're trying to find its change in y divided by its change in x. Now since we've got a straight line, the slopiness of it is pretty constant. So if we can find the slope at any given point, it's the same as for everyone. All right, so what we want to do is we want to pick a couple of spots in our line to start with. So here's the process. We try and find ourselves a nice little handy spot somewhere. So actually here's pretty handy, but that's a point we've already plotted. Let's try and find one that we haven't. Yeah, there's not too much. Ooh, that's good. We'll do that later. Right, we'll start with down here because 0, 0 is pretty good, isn't it? Right, and that's a point that we could use. It's going to make drawing stuff a little bit awkward for me, so I'm not going to use it. So I'm going to go up to this one here. So there's point 1. Okay, I'm going to use that point. It's one that I've already plotted. It looks like a nice one. We'll use it. And then we'll use another point a little bit later on. It looks handy. Now we want to go more than halfway up our line for this one. We want a nice big distance between these two random points. Now notice I'm putting this one in here. There was no point pre-plotted there. Anywhere on my line will do with this. Okay, and once I've got 2 points, what I need to do is I need to make a right angle triangle with these as my corners that aren't on the right angle. Okay, so I'm going to draw a little line down here, and then I'm going to draw a line across here. Okay, and I've got myself a right angle triangle going on there. Is that alright? So the distance across that it goes we call our run, or delta x, as I would prefer to call it, but we'll call it the run for now. So that's our run. My graph's a little bit heavy. There we go, that's nice. Okay, and then up here, this is our rise. Okay, so in my graph, my rise here is, how far did I go up? So I start down here, this is 3, I know that because I plotted it at 3, and this is 12. Okay, so it goes up to 12 from 3, so the rise is 9. Happy enough, everybody? And I'm going to draw this, I'm going to write this on my graph. Write this on my graph. My run over here, this goes from 5 across to 20, so it's 20, take away 5, which is 15. Alright, so I've got my rise, I've got my run, I can now calculate my gradient. So let's go and do that. So my gradient is equal to my rise over my run, so the gradient equals my rise, which I think was 9, didn't we say? 9, divided by my run, which was 15. So my gradient then equals, now you can do this in your head, but I recommend in an exam situation, reach for your calculator. Okay, it's weird how things go wrong in your head when you're trying to do fractions and pare them down. But 9 over 15 is what? Divide both of them by 3. It's 3 over 5, which is 0.6. Alright? Happy with that. So 0.6 is my gradient. That's lovely. So I've now got my gradient is 0.6. I'll just draw a wee box around that, make it stand out a bit. There's my gradient. And I've got my y-intercept as 0. Whoop-de-doo. Yay. Nobody cares. Except that we can now use this and pop these numbers into this equation. Right? So instead of now being y equals mx plus c, what we have is that y equals, instead of m, our actual gradient, 0.6, x plus our y-intercept, 0. Which in truth we wouldn't bother putting in, but we're doing it impressively. Now, I don't expect you to be jumping out of your seats in this one, because that's still not a thing. Nobody wants to be told y equals 0.6x plus 0. But then, we're not quite finished yet. Y is the thing on the y-axis. We can do one more substitution. The thing on the y-axis is b equals 0.6. The thing on the x-axis is a, and the plus 0 we can ignore. And suddenly now, if you were vaguely interested in the relationship between b and a, you now can solve b for any value of a ever. That if you take a and multiply it by 0.6, you will get a value of b. And let's just check that out. Okay, 5 times 0.6 is 3. Grab your calculator, do it. 10 times 0.6 is 6. 15 times 0.6 is 9. 25 times 0.6 is 15. But more importantly, much more importantly, 100 times 0.6 is 60. And I now know that. I now know that. 9,000 times 0.6 is 5,400. I don't need to draw the graph. I don't need to make a bigger graph. I don't need to guess it. I don't need to continue the pattern on. I have this relationship, and provided this remains true, it's there forever. Okay, this is for year 11, Roma. I saw you in the chat. So that's cool. Thanks very much for the people that are grabbing on. Okay, so this is how the gradient thing works. And this is how y equals mx plus c works. All right, is that okay? Now, in the description below, you'll see link. There's a little assignment. There's one of these to do, and draw them and try and get that yourself. The important thing: make sure your points are far away from each other. Get your rise, get your run. Write it on the graph. Draw everything on the graph. Keep organized. Have y equals mx plus c. Have it labeled so you know what you're talking about, and then you don't make mistakes. This is a really good example of staying organized mathematically gets you the better answer. And I'm talking to the fellas here, broadly, actually, that this is not a case of get the answer and move on really quickly. This is a case of show me all your working, score all the points so that you're not going to make a mistake, because there's lots of places you can go wrong here. All right. Okay, so moving on then, we have to deal with it. What happens when it's units? What happens when they tell us the equation to start with? Okay, so let's try a slightly broader question. Let's try an exam style question. So an exam style question says Jimmy, of course it's Jimmy, thinks that J and F are related by the following equation. Jimmy doesn't get out much. Proper scientist, sits in his room, contemplates life, plays Fortnite. Okay, so let's say that he thinks that J is equal to NF squared plus T. T's horribleness. Let's call it plus P. Right, now if you're in an exam situation and you see this equation appear, there is a small brown stain appears in your trousers for this one, because you've never seen this equation before. Now, this is not on the year 11 course, and you're, I've never seen that, I don't know what I'm doing, help. But the key thing here is that Jimmy thinks they're related by the following equation, and there will be a table somewhere later on. So let's get a good old table for Jimmy and what he's got going on. And he'll have this, he'll have J measured in whatever J is measured in. So let's call it meters for the sake of it. And then we'll have F measured in let's call it seconds. Okay. And then you'll have values for J, which will be kind of like 0, maybe not 0, 1, 2, 3. We'll keep things nice and simple. 1, 2, 3, and 4. Okay. Values for F, on the other hand, will be a little bit messed up. okay, they're going to look really weird. They're going to look like things like 2.24, right? And then the next one will be, let's pick something really odd here. I'm not picking anything random actually, to be honest, but I'm trying to make the point that it's going to look weird. So what, 3.16, for example, and then we'll try next one along 3.87, and the next one along we'll try to have 4.47. Okay, so that looks like fun. There's no great pattern here. You can't figure out what's happening here. It's going up by like 0.9, then it's going up by 0.7. It's weird. Just all over the shop, this. Then there'll be a blank column here that'll say f squared. And what's it measured in? Alright. And if you've got f squared, well, f squared is f times f, which is seconds times seconds. So it's going to be measured in seconds squared. Right. And if you go and get f squared, you go and put 2.24 into your calculator and you square it, you're going to get around about 5. 3.16 squared will give you about 10. This will give you about 15, and this will give you about 20. Okay, so that's looking a bit more promising because we've got nice regular increments here, we've got nice regular increments here. This looks straight liney. It looks like these two things are related to each other. So grab your graph and you'll plot away. Woo, away it goes. And this one actually, it won't go through 0. I'm not getting my grid out because we're at 23 minutes past. We've got 7 minutes left. I don't want to keep you around longer than I need to. So you end up with this type of thing going on here. And you'll be told to plot j on the x-axis, so let's do that. Okay. And you'll plot j, and you'll put the unit in, of course, which is j in meters. See the slash there? That means what the unit is this time, okay, rather than per anything. And then up the side you'll put f squared, which is measured in seconds squared. Well, that's great. And now we've got a graph that's a straight line. And if it's a straight line graph, it is y equals mx plus c. That has to be true. Any straight line graph you ever draw, ever, will conform to this y equals mx plus c kind of thing. And this is just a template. Remember that y doesn't mean anything other than what's on the y-axis. Okay? And in fact, you wouldn't have been told to draw it this way around. You've been told to draw it the other way around. I'm just noticing that now. Apologies. So we plotted j up the side and f squared along the bottom here. Okay? Alright, so what's on the y-axis? What's on the y-axis? J is on the y-axis, isn't it? Yeah. So the thing on my y-axis is j. I'll get a wee arrow in going on here. Okay. So j is on my y-axis. Now I've got j equals what's x? Okay, it's the thing on my x-axis. So what's on my x-axis? That's f squared. Isn't that right? Yeah, f squared is my x-axis. Just check down there. I moved it to make sure I made this point right. Plus c. Oh, you're feeling great about this now, aren't you? Well, wait a minute. No, wait a minute. Something's cool here. Because if I take this equation here, okay, I'm going to bring that down and compare them. Well, we've got a j here and here. Let me get the wee highlighter or get my colour pen here. So j goes from there to there. F squared goes from there to there. I've got the gradient here, and I've got like n here. And I've got the y-intercept here, and I've got p here. And this is called comparing the equation. What I've actually discovered is, because I've plotted this line and it's turned out to be a perfectly straight line graph, that if I go and find the gradient of this graph, I will actually get n. Okay, because the gradient is the thing that's stuck to f squared, so the gradient is n. And the y-intercept is the bit that's hanging out the end here. So the y-intercept is p, which is kind of handy. Which is a kind of handy way of getting things. Okay, so now what I need to do is I need to go and make that calculation. I need to go and mark some stuff off, get my marker out, go pick that off there, pick that out there, and then make my right angle triangle. Now I need to do this on gridded paper because I need to get my rise, I need to get my run, I need to calculate my gradient, and once I calculate my gradient I will have a value for n. right? Which is just the same as I've just shown you. Exactly the same process as I just showed you. Find your rise, find your run, get a value for that, and you'll get a number. Okay, so let's imagine that we have, you know, like we end up getting rise over run, so rise divided by run, and we can make a fair estimate of this. Right, so equals, let's say we have a run of 2 divided by a rise of 10, which is around about right actually. Well, a run of, yeah, around about that. Rise of 2, run of 10. Okay, do that division, and I'm going to end up getting a gradient which is equal to 0.2. And this is the important bit. It's not actually 0.2, because this time I have units on my axis. So my rise is actually 2 meters, and my run is actually 10 seconds squared. I've just chosen to ignore them and focused on the numbers, but I can't keep doing that forever. I have to deal with them at some point. So that leaves me with 0.2, because I did 2 divided by 10, but I've failed to deal with the meters divided by seconds squared. Okay, I really should have done that in red, but anyway. But the meters divided by my seconds squared is my unit. That's where units come from. That's why some units look really weird, that it's 0.2 meters per second squared. The per sign, the slash, actually means divided by. It's the leftover bit from when you do a gradient calculation or when you do all sorts of things. Alright? Are we happy? So that's 0.2 meters per second squared. So my gradient n is equal to 0.2 meters per second squared. This is a very common exam question that would give you this and would say find the constant n and then give its value. And there's a question like that in the assignment question, once again in the description below. And the last thing we then have to do is find the value for p here. And since we've compared it to this equation, p is the y-intercept. So all I need to do is go over here, look at this point here. When x is 0, what is y? Alright, and in this one it's probably 0 as well. In this one, but all you need to do is pick it off the graph and go, right, okay, let's assume that it's like 17. It's not in this case, but let's just assume it is. Then your y-intercept is 17. So p is equal to 17. But again, it's not just 17, because what is the value? It's not 17, it's 17 meters. So p is 17 meters. And that's all there is to it, really. That's how you do y equals mx plus c graphs. Now, as a last tip, what I tend to do, what I tend to suggest to my students is, when you find this question in your exam paper, be it in the practical paper or in the main theory paper, once you see an equation that you've never seen before, right below it, y equals mx plus c. It's almost certainly going to be about that. And then draw lines. Okay, this is the thing that I'm going to plot on my y-axis. This is the thing I'm going to plot on my x-axis. And if you don't know, take a look down at the table. Right, the table will tell you. There's J, there's F. Well, there's no mention of N in my table, so it's F something that's getting plotted. So therefore, my gradient is going to be N, and my y-intercept is going to be P. And I can play that game all day long. And I'm happy with it, because I'm going to get 5 marks for plotting the graph, and I'm going to get 3 marks for finding the values of N and P, and I'm probably going to get a mark each for their units. Right, so I just banked 10 marks and walked away, you know, moonwalk out of there, happy all the way. Take it to the bank. Okay. Hi sir, you can get a c-intercept. No, sorry, an x. Yes, you can get an x-intercept. No, sorry, I saw the correction here. You can get an x-intercept. That's if the line travels down through here and hits the x-axis. It's not really a thing though. It's not really a thing. It's not massively useful. It's maybe useful. There's an experiment where you calculate what absolute 0 is, and the line extends all the way back and hits the x-axis back here. But it's not overly significant when we're dealing with straight line graphs on that one. Okay. Any other questions before we sign off for the evening? That's graphs. we would ideally then do kind of rearranging equations and so forth. If you want a stream in that, pop a comment down below. Otherwise, our next one will be in 2 weeks' time, and will probably be on vectors and scalars. Okay, so thanks very much for tuning in, everybody. I really, really, really appreciate it. Have a great night, and all that remains for me to say is, don't forget, physics rocks. It's true. And of course, we can't go without giving a shout out to my best fans, my what were last year's year 8 maths class. Okay, so hello to all the people who are now year 9 maths who I don't get to teach anymore. I'm missing you. I'm sure you're actually understanding some maths a bit better now that you have a better teacher than me. But take care. 9E shout out.